So I think hopefully everybody knows the distance formula. If not, I made it just on one slide. So distance equals rate times time. This just means if I'm, say, driving at a certain speed, say 30 miles an hour for 3 hours, I'm going to go 90 miles. It's actually amazing how often this is the correct answer to a question, or the correct way to solve a question, if you can recognize what you're going to think of as distance, what you're going to think of as rate, and what you're going to think of as time. This form of the distance formula really only works when the rate is constant across the entire time. But now that we can integrate, we're going to be able to allow that to change a little bit. So it provides intuition for a lot of problems, and all that we're really doing is imagining rate on one axis, time on another axis, and then the distance you're going to cover is going to be equal to this area. So that's just the definition of the area of a rectangle, is height times width. So let's look at something I call the job problem, which seems to give a lot of people quite a lot of trouble. So I take my motivation quite often from The Simpsons. So I said, if Lenny can do a job in 6 hours and Carl can do the same job in 4 hours, how long does the job take if they work together? A lot of times when you ask people this question, they will say something, the first number that pops into their head is 5 hours, which seems to make sense because it's just the average of 4 and 6. But that would actually mean that by helping out Carl, Lenny's making the job take longer. So, clearly that's not the right way to think about the problem. And the right way to think about this problem is that it's the rates that are additive. So Lenny, if he can do a job in 6 hours, he can do 1/6 of the job per hour. And Carl can do 1/4 of the job per hour. So if they're working together, their rate is going to be 1/6 plus 1/4, and that ends up being 5/12 of the job per hour. And so here, the job is what's going to end up being the distance, and the time is what we're asking for. How long does it take them to do the job if they're working together? So solving for time, I just get distance divided by rate. And then I've worked out what these numbers are. We have one job. The rate that they're working is 5/12 jobs per hour. I can multiply the top and bottom of that by 12/5 and get 12/5. So the job is going to take 2 hours and 24 minutes if they work together. But we've still made the assumption that Lenny and Carl are working at a constant rate. So suppose instead that Lenny works at a rate L of x and Carl works at a rate C of x. Then my conditions that I started out with, I could rewrite these in terms of definite integrals. So I know that if I let Lenny work for 6 hours, he's going to finish one job. So that means that the integral of L of x from 0 to 6 has to be equal to 1. And then, now I've confused my L's and my C's. So I think this should be the C. And the integral from 0 to 4 of C of x should also be equal to 1. And that's just the way of mathematically writing down the condition, or the statement, that Lenny can do one job in 6 hours and Carl can do one job in 4 hours. And so now my job question is, can I find a capital T, so that's a time, so that when I add these rates together, I get 1. And so now this is not quite as nice a problem, because there are actually a whole bunch of different rates that I could add together that would give me this condition. So for instance, I could just say, well, I guess I can't. So I have some constraints too. So I'm bound by the constraint that Carl works at this rate. So the integral of that one has to be over 0 to 4 has to be 1. And the integral of L of x over 0 to 6 also has to be 1. So I just invented some functions to try and demonstrate this. So I chose 12 minus x divided by 54. And all this is going to do is when we're at time 0, so when x is 0, I'm going to have 12 minus 0 divided by 54. And at the end of the job, so when x is equal to 6, I'm going to have 12 minus 6, which is going to be 6 divided by 54. And we can forget about the bottom, because that's the same. So at the beginning, we have 12 over something, and at the end, we have 6 over something. 6 is half of 12. So all this is saying is that Lenny is working twice as hard at the beginning of the time period as he is at the end. So he gets tired while he's working. So by the end of the 6 hours, he's going only half as fast. And then I just have to put this 54 down here so that the condition, the constraint that he finishes the job in 6 hours is met. And then I'm going to do exactly the same thing for Carl. So initially, he's working at 8 over 24. At the end of his 4 hours, he's working at 4 over 24. So he works faster, so he's also getting tired faster. And now, how long is it going to take them if they work together? So would it be more or less than the 2 hours and 24 minutes? So basically what I want to do is find t so that when I integrate this function, L of x plus c of x, from 0 to t, I get my one job finished. And so I'm just going to start by plugging in the two functions. So L of x was 12 minus x over 54, and c of x was 8 minus x over 24. And then I don't like having these numbers in the denominator. So I'm going to multiply both sides of this by 216. That's going to be 4 times 54. So it'll be 4 times 50 is 200. 4 times 4 is 16, 216. Or it'll be 9 times 24. You can do that in your head pretty easily, too, because 10 times 24 would be 240. And that's 24 more than 216. So that's got to be 9 times 24. And so that's going to get everything out of the denominator. So mostly the reason I wanted to do that, it makes the lines a little skinnier so it all fits on one slide. But it also means that I can now add these together, so my integral is going to simplify itself a bit before I actually have to compute an antiderivative. And so what I end up having to compute the antiderivative of is this function here, 120 minus 13x. So I can just use my anti-power rule to get that. And that's going to give me 120x minus 13 over 2x squared from 0 to t. And now even though the variable t is on this side, I treat it exactly the same way. So I'm just going to evaluate my antiderivative. So I have my antiderivative here. I'll evaluate it at t, and then subtract it, evaluate it at 0. So I get 120t minus 13 over 2t squared. And then luckily on this side, since I've got it at 0, when I plug in 0 to this antiderivative, I just get 0, so that makes things a little bit simpler. So I end up with 13t squared. So I multiplied both sides of this by 2 as well. 13t squared minus 240t plus 216. Oops. I think I forgot to multiply that bit by 2. And then you can solve that using the quadratic formula. And that gives 57 minutes. Although I think it gives 57 minutes for this one that I forgot to multiply by 2. So I'll have to check that. And then another application where this is going to turn up, for those of you who are taking 461, in the next couple weeks we're going to learn about something called a probability density function. So I'm going to denote a probability density function for a random variable x just as f sub capital X, and its argument is going to be little x. And I'm going to use it to assign probabilities to a random variable being in an interval. So I'm reading this thing on the left-hand side as the probability that my random variable is in the interval AB is just going to be the integral of my probability density function over the interval AB. The support of a random variable is just going to be the set of points. So generally, it's an interval. A set of points S where the probability density function is greater than 0 when x is in S. And so some of the properties of a probability density function are if f sub x is a probability density function, so I'm going to abbreviate that as PDF, then I have to have f of x is greater than or equal to 0 for all real numbers. And when I integrate this, so sometimes instead of writing an interval as just from A to B, I might want to write a set that might be made up of more than one interval. And so in that case, when I've defined S to be a set, so here S is the set of points where this thing is strictly greater than 0, I can write the integral sign, and I'll just put the name of the set at the bottom. And the integral has to be equal to 1. So the exercise that will show up quite often is, can you prove that a certain function is actually a probability density function? And so I'll go through one example of that pretty quick. So the PDF of a beta 2-2 distribution is defined to be 6x times 1 minus x when x is in the interval 0, 1, and it's defined to be 0 otherwise. So if I want to verify that f of x is greater than or equal to 0, that should be pretty straightforward. If I have a number between 0 and 1, then it's greater than or equal to 0. So 6x has to be greater than or equal to 0. And 1 minus x, so the smallest this could be, is when x is equal to 1, and that's 0. So it's pretty easy to verify the first condition. The work is usually verifying that the PDF is going to integrate to 1 over its support. So here I'm going to have the integral. So S is going to be 0 to 1. So it doesn't actually include the endpoints, but those end up not mattering for the integral. So I'm going to say this is just the integral from 0 to 1 of 6x times 1 minus x, oops, so again a typo, dx. So this x shouldn't be here. Hopefully that's going to go away. And so using some of the properties I've listed in the first set of slides, I can think of x times 1 minus x as my f of x. And so I'm just multiplying that by a constant. So I can take that constant outside of my integral sign. It'll make things a little bit simpler. And then I'm going to just go ahead and do the multiplication. So I have x times 1 gives me x. And then x times x gives me the x squared here. And then I can calculate the antiderivative of that, just using my anti-power rule on each term. So the first one came from 1/2 x squared. And the second term came from 1/3 x cubed. And now that I've written down my antiderivative here, I've moved my limits to the right-hand side. So it means this notation, again, just means evaluate my antiderivative at the upper end point and subtract the antiderivative evaluated at the lower end point. So again, because I have an x in each term, the bottom end point's just going to be 0. That simplifies things quite a bit. So I end up with just 1/2 minus 1/3. Oops. And that's equals, so 1/2 is, I could write that as 3 over 6. 1/3 I could think of as 2 over 6. So 3 over 6 minus 2 over 6 is 1 over 6. And I have this 6 out in front, and that cancels each other out. So I verified that this function here, fx of x, is a valid probability density function.